So, in this lesson I'm going to talk about how to make the characters thrive and die, how to interact with other objects, and how to build an inventory system to hold the items we pick up along the way. The player progress and life of Robo will be calculated around three aspects: the energy, the mechanics, and the memory. The energy is the battery of the robot. The drainage can depend on the effort of the robot. Walking can make the power to drain faster compared to idling, but for now let's keep the system simple and only use time as the main counter for the battery. If the robot is alive, the battery is going down. The mechanics are related to the moving parts of the robot. When it moves, mechanical wear will occur. The memory is related to the background story. His half-human mind is stressed about his condition and starts to have corrupted sectors. Every time the battery goes down or the body suffers some mechanical problem, the mind starts to decay and lose its integrity. What makes the game end immediately is the battery. If the robot has no power, no processing will happen and the robot is dead. The player needs to make everything in its power to keep the battery with some charge. Same can happen with mechanical problems. If the player loses the ability to move, it may not be possible to reach a charging point in time, and eventually die. On the other hand, losing his mind will just affect the way he sees the world. This behavior is actually the most difficult to implement, not because it depends on very complex code, but because it implies the assets to have many different sprites in order to change them. So, to keep this series short and simple, I'm not going to address that, and the memory bar will only go down with no consequences. Let's create a script called RoboHealth and add it to the prefab. On a side note, if you change something in the prefab on the project panel, the original source, the change will propagate to the others in the hierarchy. But if you add something to the clone in the hierarchy, it will be unique. If you do it by mistake, you can select Override and click on Apply All. This will make the original equal to the clone and consequently all the same. We need three variables to hold the information about the character's health in a normal script like all scripts we did until now, but to get these numbers outside the character, we will need some references. Remember? Creating a GameObject variable, dragging the robo there, the get component, etc. etc. While this is not wrong, it is also not the best way to do it. And it would be much easier if those variables were in some place that any object could access directly without the need to reference each other. Because let's say, the character needs to work with those variables. The UI interface needs to read from them to show you the values. The enemies or items could affect the values directly, because attacks or power-ups, I don't know. There are many situations where you need to read or write from and on those variables. Imagine a situation where all enemies can decrease the player's life by being close to him and you have 50 different enemies. All of them need a reference to the robot, but not the prefab, the actual robot in the scene, so you cannot prepare those prefabs before instantiation and you need to do it on the runtime, and if you have more than one character you need to change all of the references. It's not impossible, but it's not the best way. So, what if we could have those variables outside of the character and the RoboHealth script just access them remotely and write on them? Any other object that needs those numbers just has to access the same variables, and they can do it even if the robo is not present in the scene. This prevents a lot of problems where there are hundreds of potential references in a game, which in a survival type would be, but also in many others. There are several different ways to have the variables centralized. Using the built-in PlayerPrefs is one of them, or building a save and event system and directly accessing it to change the values. Well, this is actually my favorite one, but is a more advanced topic. Because this is a beginner's lesson, I will use another technique that is in the middle, the usage of a scriptable object to hold information. A scriptable object is like a virtual object that lives only in the project folder, and you cannot add into the scene, but you can reference it from anywhere. Its variables are persistent, meaning the values will stay between scenes, and you can have multiple copies of the same scriptable object, with different names of course, to hold data for different characters, like the main character and all the enemies and bosses. You make a scriptable object by scripting a class that inherits from the scriptable object main class, instead of the mono behavior. Then you set up a menu to create the scriptable object, and after you create it, it is available to all other scripts with a simple reference. So, to make our RoboHealth script have some shared variables to work with, let's first create that scriptable object that holds the data. Inside the scripts folder, create a new subfolder called Scriptable Objects. And inside, create a new script called CharacterHealth and edit it. This will be a very simple script. First, we can delete all the methods and make it inherit from the scriptable object main class. Public class CharacterHealth, scriptable object. Next, add the variables. Public float energy, public float mechanical, and public float memory. Everything needs to be public in this script in order to be accessible to all others. The script is done, but the class needs some attributes to allow the user to create the object in the project panel. Before the class, code this: create assets menu, file name equals CharacterHealth, menu name equals game assets / CharacterHealth. As you may get from these commands, a menu entry will be created in a specific location and with a specific name. This sets the menu, this sets the default name when the user creates the scriptable object, and this sets the location. Once done, save and return to Unity. After compiling, if you right-click on any folder on the project panel, you will open the contextual menu, but now you have this new option up here. As you can see, it follows the structure set in the class attributes, and if you select, you will create an object with the set default name. If you select it, you see in the inspector the three variables, and you can put 1, 1, and 1 in every field. Well, that's it. The scriptable object is just this. Once again, you cannot add it to the scene, and it does nothing unless holding values. Now, for this to be useful, you need to reference it where you need these values and use them. So let's edit our RoboHealth script, the ones that governs how the robo lives and dies, and let's start by adding a reference to the scriptable object. Serialize field, CharacterHealth, health, where CharacterHealth is the type of our scriptable object main class. It needs to be present in the inspector, so we can drag the scriptable object there, with health as name. Here, every time we need to access the data inside, we just need to type health.energy equals 1, health.mechanical equals 1, health.memory equals 1. Here we are actually setting the values to 1, our maximum, in order to make the robo have a full life at the start of the game. Every calculation will happen between 0 and 1. Now, in the update method, if we code health.energy equals to health.energy minus 0.001f and run the game, we can see the energy variable going down. Our robot is discharging his battery. A simpler way to write this is health.energy minus equal 0.001f. This minus equal operator is a simplification of the code above. It does exactly the same thing, and you just need to type less code. So from now on, we are going to use this technique to increase or decrease numbers, and we can just delete the previous line. Because all computers are different, let's make the decay ratio be the same in every machine by using the frame time to calculate the amount. So 0.001f multiplied by time delta time. And to make it more configurable in Unity, let's add a variable to hold this 0.001f. Serialize field float energy decay equals 0.1f. Now the number doesn't need to be so small because of the time delta time. And in the calculation line, change 0.001f to energy decay. Save and return to Unity to play. As you can see, now we can easily set the decay ratio and adjust the difficulty of the game here. Because we are multiplying by time delta time, this number represents the amount removed every second, so 10% every second is quite fast. To keep the setup even easier, let's divide by 60 and transform this into decay per minute instead of decay per seconds, and add a comment to future reference. Energy goes down in a steady pace, value per minute. Health.energy minus equal to, open parenthesis, energy decay divided by 60f, close parenthesis, multiplied by time delta time. Now, every minute the robot loses 10% of charge, meaning you have around 10 minutes to recharge the battery. Now we make the mechanical health value go down. We need a variable to hold the input from the player, vector2 movement, and another to hold the configuration value, serialize field float mechanical decay equals 0.1f. We start by getting the input from the player, movement x equals input get axis horizontal and movement y equals input get axis vertical, and then decrease the mechanical value if movement is more than 0. If movement magnitude is higher than 0, so it's moving, health mechanical minus equal to mechanical decay divided by 60 multiplied by time delta time. Here we use the same trick to make the value per minute, and then we comment for future reference again. Makes mechanical health go down every time it's moving. If we go to Unity, we will be able to see these values go down, energy based on time and mechanical when we move the character. You can right-click on the Scriptable object and choose Properties to get an individual inspector for it. Dock it next to the console to have constant access to the values, even while you are setting other parameters in other objects. Now we are just missing the memory value. This will be referenced to the energy and mechanical levels, but not when the character has good numbers. We want the robot to be afraid when it feels the battery is too low or the body has some mechanical problems. This means we will only decrease the memory's value when the other two are lower than a specific threshold. To do that, we need two variables to configure these thresholds. Serialize field float mem by energy level equals 0.8f, which is 80%, and serialize field float mem by mech level equals 0.9, which is 90%. In the update, we code two lines, one for each other variable. If health.energy is lower than mem by energy level, health.memory minus equal memory decay divided by 60 multiplied by time delta time. And if health mechanical is lower than mem by mech level, health memory minus equal to memory decay divided by 60 multiplied by time delta time. This means that the memory will only decrease after the energy gets lower than 80% and also the mechanical value below 19. The script is done and ready to work, but to help the level designer or the game designer to operate these variables when constructing the game, let's add some tooltips to the inspector. Before the variable, you can help the user by writing about the purpose of the variable. So let's do that for all of this. Tooltip: this mechanical decay will be applied every time the character moves. Tooltip: this memory decay will be applied twice if mem by energy decay and mem by mech level are below the threshold. Tooltip: level of energy at which the memory starts to decay, and tooltip: level of mechanical at which the memory starts to decay. If you save and return to Unity, you will see that these variables now have this message to guide the user. This system is working, but if we lose energy, we also need something to make that energy go up again, or we will die very quickly. I guess we can pick up some items to recharge the robot's battery. In this new asset, you have these new little sprites. For now, we will need plutonium and another one like lithium, for example. Set the sprite to 300 pixels per unit and as a multiple sprite mode. As the others, set the max size to 4096. Edit the sprite and set two rectangles around the elements. The blue one is lithium and the red one is plutonium. Apply and exit. Now drag one sprite to the hierarchy and add a polygon collider 2D to it. Keep the polygon simple, just 4 vertices aligned with the base of the object is enough. Set it to isTrigger and it's done. You can drag the lithium to the prefab folder and delete it from the hierarchy. Do the same for the plutonium. This isTrigger option will make the collider behave differently. Other colliders cannot physically collide, drag, or get obstructed by it. It's not physical, but it can still be detected and its area calculated as a collision. This means you will not be able to physically collide with the plutonium like you collide with a tree, but Unity knows you are touching the plutonium. Our script will receive a message every time a trigger is triggered, and we can use that message to run specific code, including code that affects the object we collide with. So let's create a new script, call it RoboInteractions and drag it to the Robo's prefab. This script will detect triggers and act on them. And in these lessons, let's keep the interactions to a minimum. If you touch the item, you pick it up automatically. So, remove the update method, we don't need it, and add a new one with this exact name. Void on trigger enter 2D, open parenthesis, collider 2D, space other, close parenthesis. Pay attention to the capital letters. It's very important to keep this exact spelling. Inside, let's just print other to see what happens. As you can see, the print is printing the collider 2D of the object. Why? OnTrigger enter 2D will run every time a collider or trigger in the same object collides. This method is expecting one argument of a collider 2D type. When the collision happens with the trigger, the other object that has the trigger will be sent to this variable. This means you have access to the other object collider 2D directly here by calling other. So if you print other, you can see others in console. Of course, if you have access to the collider, you can easily call the game object behind the collider. One thing we can do is destroy the object. If we pick it up, it disappears. But also, if we pick an item, it should go to the robot's inventory. This will allow the player to collect items in the game and do other stuff with them when playing. But to add an item to the inventory, we need to create a script to hold the inventory and some functions to manage it. This item will need a script to hold some information about the item itself. We can actually improve the script over time as we need more and different information about the items. For now, we just need the name and the energy level. So create a script called ItemProperties and add two variables. Note this ItemProperties script will be used in every item, so the variables need to be kind of generic. Inside, just code public string item name and public float energy. Save, return to Unity and add it to the items prefab. In the inspector of the prefab, set the name exactly equal to the prefab name itself. This will be a future reference to the original name of the prefab. Because every time you add a prefab to the scene, the name will have a suffix and cannot be referenced correctly by it. In the plutonium item, you can also set the energy value to 0.2F to eventually be used later. The items are ready and we can start to make the inventory. Create a script called inventory and start by adding some variables. Public string inventory name. This is just a human reference because you can use this in many objects that need an inventory. Public int max slots equal 10. This will be the size of our inventory. And public int max stack size equals 5, which will be the number of individual elements inside the same slot. Let's say in every slot you can have up to 5 lithium items, for example. Now we need an array to hold all this information. So, public item, open and close square brackets, items. This item type does not exist, it will throw you an error in the console, but we can solve that by building a struct with the information we need. In this case, we need the name and the quantity of each slot. So, public struct item, open curly brackets, and inside we have public string name and public int count. To make these available in the inspector, we can add system serializable before the struct declaration. Now that we have all the variables we need, we start by setting the array. I will use, for the first time in these lessons, the for loop to do that. A for loop is a conditional iterative statement. It's normally used to count from one value to the other, and every time that number increases or decreases, many actions can be performed. We are going to use this to count every slot of our inventory and set it to empty. First, we set the array to a new clear array with max slots of size. Items equals new items, max slots. And then we go to each slot and set a default name. For int slot equals 0, slot lower than max slots, slot ++. Int slot equals 0 declares a temporary variable to be used as a counter. Slot lower than max slots is the condition for this to happen. And slot ++ will increment the number by 1. So slot starts at 0, and because it's lower than 10, the code inside the curly brackets will run. Here we will set up the name to empty, not because it is necessary in terms of code, but because it is more humanly readable. Items slot.name equals empty. We don't actually need to put the counter at 0 because we just have created the array, and by default is 0. We use the slot variable to iterate the array. In the first run, we can read this as item0.name equals empty. Then the statement reaches the end and it does the final operation, which increases the slot variable by 1. 0 plus 1 is 1, and the test begins again, because now 1 is lower than 10. So the code inside will run again. Now you read this as items1.name equals empty. And the process repeats until the condition is false. When the slot is no longer lower than 10, the for loop code stops running and the script continues. This is the typical usage of a for loop statement. Save, return to Unity, and add the inventory script to the RoboPrefab. In the inspector, you can set the name to RoboInventory. Now select the robo in the hierarchy and play. You will see the start method creating all the empty slots. So far, so good. We have an inventory, but no way to add or remove items to it. We can do that in many places, but the most general and widely available place is inside the inventory script itself. So let's create a new method that handles the process of adding an item to the array. Public void add item, game object to add. This public method is expecting a game object, then eventually we collide with an item and the item will be sent here. But more on that later. With the object here, we can perform many operations or just ignore it. Eventually, we will ignore it if we cannot pick any more objects because the inventory is already full. So every time the add item method is called, we need to check 3 things. Is there an item with the same name? If yes, does that slot have space for more? And last question, if the others are negative, is there any empty slot to add this new item? By checking these 3 states, we are actually preparing the inventory to receive the item. But if all of those questions return false, that means the inventory is full and we just ignore the item because we can't pick it up. So, we will need a variable to hold a temporary value of the potential index in the array. Int working slot equals -1. The default value is -1 because 0 is the first index of the array, so -1 is completely outside of the array. We are declaring the variable here because it's not needed anywhere else, and also because it can be destroyed after the work is done, so we don't need to waste memory with it anymore. We will also need another variable to get that name from the item properties. String item name equals to item to add, the game object, dot get component item properties dot item name. We will use this name not only to eventually add the original name and not the clone name, but also to compare it to the names already in the inventory. Find a slot with the same name. For int test slot equals 0, test slot lower than item's length, the size of the array, test slot plus plus, open curly brackets, if items test slot dot name is equal to item name and items test slot dot count is lower than max stack size, open curly brackets, working slot equals to test slot, and break. We use a for loop to go through all slots and compare the name in the slot with the name of the item to add. At the same time, notice the AND operator, we are looking for available space inside the slot. If the name matches and the space is lower than the maximum, we run the code where we set the working variable to the number of the slot we are testing. After this, we break the for loop and we will add the item. So to do it, add item to working slot and remove it from the scene. If working slot it's not equal to -1, which means we found another number, items working slot dot name equals item name, the name goes here, and items working slot dot count plus plus, we increase the count by 1. At the end, destroy item to add. This will remove the object. Just to clarify, this number here will only change if there is available space in the slot. If there is no space, we will not add and delete the object. But this script is not fully working yet. There is another case to check. Imagine you have a slot with the item name, but it's full. We still have more empty slots, but because they are called empty, the name does not match and no item is added. So we also need to account for this situation where we didn't find any slot with the same name. So we also need to account for this situation where we didn't find any slot with the same name or with available space. For example, you pick up the 6th lithium item and already have 5 in one slot. In this case, we need to add the lithium to an empty slot. To do it, before the code to add items, we write add item to empty slot. If working slot is equal to -1, for int test slot equals 0, test slot lower than item's length, test slot plus plus. Inside, if item's test slot dot name is equal to empty, working slot equals test slot, and break. The first thing to test is if there is a change in the index. If it is still -1, it's because the finding for space in name slot didn't find any space. And because of that, we are now searching for a slot called empty. If we find one, we set the working slot to the number of the one we are searching and break out of the loop. After this, we add the item to that slot. In case of no empty slots and slots with the same item but full, the number stays -1 and none of the code runs, meaning no adding to the inventory. Let's save and test this. Now, the final detail to make all of this work is in the script that handles the trigger collision to call this addItem with the object to add. We return to RoboInteractions and delete this print. Now add a reference to the inventory, inventory. Careful with a capital letter, the first one is the type, is the class. And the second one is the name of the variable in this script. And get that component. Inventory equals to get component inventory. Remember that both scripts should be in the same object, the RoboPrefab, and you don't need to drag nothing to a variable. Get component will be enough. Now inside the onTriggerEnter2D, add this line, inventory.addItem other.gameObject. We call the inventory and run the addItem method, and we put the other gameObject inside it. This will send the gameObject directly to the inventory script. So, to add an object to the inventory is as simple as this, but to prevent adding a rock or a tree, we should make sure that only items can be detected. We can use the tag system and just perform this command if the tags match. We need a reference for the name of the tag, serialize field, string, tag to detect equal item, and an if statement to test if the object has that tag. If other tag is equal to tag to detect. Save and return to Unity. Before we can test, we need to add the tags to the items prefabs, or else we will not pick them up. Select the prefab, and at the top left in the inspector, select the tag menu. Click on Add Tag, and a new panel appears. Add a space with a plus button and write Item. Save and select again the prefab. Now the item tag is in the menu. Select it in all the item prefabs. At this point, you are able to add items in the world and walk around to pick them up. So let's test if the limits are working. First, I will test filling one of the slots and see if it is going to the next automatically. Okay, now let's test if the script ignores the item in case of a full inventory. As you can see, everything works perfectly and our character is able to interact by picking items in the world. In the next lesson, we are going to add an interface for these variables. We need to see the health values on the screen and what we have in the inventory. Eventually, we need to use those items, so we need to build some way of doing that. The most obvious thing is charging the battery, with the plutonium for example, but other kinds of combinations can be possible to make the player search, keep and combine different types of items in order to achieve other levels in the game. So, I hope you learned something new with this lesson and I'm expecting to have you in the next one. Bye!